All right, let's suppose we have a function, and I'm just going to draw like a random function. It doesn't even have to have an equation for now. Let's say we have a function that looks like that, and let's say I pick a point as somewhere here, and I give you an interval that is some units above and below, and the red lines here are going to be an equal length above and below, but for now we're not going to use any numbers. So envision you have this interval, and let's say you want to trap this function using a pair of horizontal lines. So you're going to have another interval so that all of the function that you contained within this green interval is contained within the red interval. To show you what I mean, let's just take, for example, something like that. As we can see, everything within this green interval, the portion of the function which I bolded is not within the interval, because we have some portion of the function, this brown portion right over here, that is below the red intervals, both of the red intervals. It's not in between the window, and so this is an invalid choice of the interval that I want to choose. So in this case, then you would have lost the game. But how can you win this game for sure? Well, a simple choice is to just reduce the length of the green interval. So let's instead pick the green intervals to be a little bit closer. Let's pick the green interval to be somewhere like that. And now we can clearly see that this choice wins, because everything in every value of the function between these two green lines is within the red interval. And as we can see, the portion of the function that is within these two green lines is marked with this new orange bold section over here. And as you can see, the red intervals constrain this function. So indeed, this is a valid choice. And we can even make this even smaller. We can make this even smaller. And we can maybe make the intervals, I'm just going to draw it in another color, another green. We can make it even smaller like that. And we can still see that the function itself is bounded by the green interval that we just drew over here. So we can just make this even smaller and smaller. And so now an interesting pattern that we can see here is that when we have an interval that is centered along this original point that I showed you at the beginning over here, if we make it smaller and smaller, the function is always going to be between the red lines. And so that's kind of an interesting game that you can play with, almost every function. So let me just give you another one. Let's make this like a squiggly, something like that. And then I'm going to give you a point right over here. And then let's say I give you a window, right? Again, equally spaced above and below this black point I drew over here. So take a moment to think about a valid choice of the interval so that you can pick it to constrain the function along these two red lines. So now, after you've thought about it, let's work through it. Let's say you draw the green lines like that. Okay, so we can see that the function is not constrained because we have some tiny portion over here, right? This portion that is highlighted with the pink is not within these two red lines. However, we can always make the interval smaller. So let's just make the interval smaller. And again, I'm drawing these intervals. I'm drawing these intervals so that I'm drawing both the red and the green intervals so that they're equally spaced. They're basically centered about the point, the black point. And we'll see how this black point has a significance over here. So let's just try this this green interval. And so obviously we can see that we have constrained our function, and I'm just gonna bold it. We have constrained our function so that it lies between the red lines that I originally drew. Okay, so this is all cool and fun, but let's try a different type of function. So I'm gonna go down here, and let's suppose instead I give you the following function. I'm gonna go up here, and then once I hit that point, I'm going to go down over here. And then, so for this type of function, it's called a piecewise function, and that's because we have two pieces, right? One above and one below, that don't intersect each other, but still define the function at all points along the x-axis here. So for this piecewise function, let's assume that we want to focus on this circle point right over here, and we're just gonna play the game again, except that we're going to we're gonna focus on this point instead of this point. However, we still must consider that when we effectively trap a function, like if we do that, then we're gonna still have portions of the function down here, right, along this bottom piece. So let's play the game again, right? I'm gonna give you the following interval. So I'm gonna give you let's say I'm gonna give you these two red lines, and then try to find a pair of green lines between to trap the function between again, and we're gonna center at this circled point. Try to find a pair of green lines centered about this circle point to trap the function, and see if you can do it. Okay, so now you might have noticed that we can trap it using like something like this. Oops, like that. Okay, and this is just like a rough drawing, but obviously, like we can make it into a very small interval, and all portions of the functions indeed do lie between these two lines, as indicated like in the bold regions that I just drew, like that. Okay, cool. What if I give you a smaller set of red lines though? So instead, let's try this set. One above here, and then one below, like that. And again, you still have to draw a pair of two lines, a pair of lines, one to the left of the brown point. I'm just gonna keep this brown point. So one vertical line to the left, one vertical line to the right, and you must trap the function so that it lies between these two red lines, and see if you can do that. So now you might have noticed that it might not be possible, because if you try something naive like that, then we can see that a portion of the function lies below the bottom red line. So it's precisely it's precisely a portion of the bottom piece, and because that piece lies below the red line, that this choice of vertical line simply won't work. So instead, let's try a different set. Let's try a smaller set. Because typically, as our sizes get smaller, our the chances of finding a good pair increases. So let's try this set. Well, again, we still see that doesn't work because we have a portion of the bottom piece that lies below the bottom red line. So that still can't work. How about let's make this even smaller. Let's try something extremely small like that. Okay. Well, we're still gonna get some bottom piece right below the red line, and that's because up to where the brown point is defined, there if you go even a little bit to the right of that x coordinate, then you're gonna always have this small tiny piece of the brown the black piece denoted by this arrow over here. And so we can actually conclude that no matter how large or how small you make this pair of green lines to be, you will never find a valid pair so that we can constrain the function, right? We can constrain the function between these two red lines. And intuitively, even if we just remove the green lines over here, we can see that since we have to pick, and this is just according to some rules that we'll see in a sec, if we have to pick a left green line and a right green line, then the right green line is always going to cover some area that isn't to the right of the brown point. So like if I draw over here, there's still going to be like some area over here that's just not covered. That's just not covered by the function. It just dips down instantaneously at the brown point. Okay, so we can't possibly win. So we can't possibly win this game if I give you this pair of red lines. So why are we playing this sort of this game with functions? Like what does this lead us to? Well, in calculus or possibly pre-calculus, you may have heard of the concept of a limit. And so a limit, right, as you may have seen, is the value a function approaches as you get closer to a certain x coordinate. So if I give you this function, and it doesn't really matter if it's defined or not, but let's just say it's a point. You want to find like the value of a function at this point, right? Then if you travel along this function and approach it from both sides, then what value will you get really get close to? And so even if this point right over here is not defined, you can still approximate it by saying, well, if I go from the left, if you keep going from the left and keep approaching this vertical line, this vertical line right over here, right? If I keep approaching it from the left and keep approaching it from the right, then approximately what y coordinate, right? Like what value over here will I reach, right? And so that's like the informal intuition that you may have learned from calculus class. But here, the reason why we're playing all of this trapping game, like if I give you, again, just to recap, if I give you a certain window above and below a point, and the point doesn't even have to be defined, right? If I give you a certain window above and below, and then you want to constrain it so that you want to constrain the function so that it lies between these two horizontal lines, right? Like, is there a valid choice? So this game is where the formal definition of a limit comes in. So as we can see, for this pair of red lines and this function, right, we can play this game. And why can we win this game. Define winning as picking a pair of vertical lines centered at this specific point, so that we can constrain the function, right? And so here we can obviously that we can win the game. Here we can also see that just with a little bit of squeezing these two lines, we can also win the game. However, here, in this third example, we cannot win the game because we've noticed that because this point is located at such a location such that no matter where you pick the right vertical line, you're gonna always have some bottom piece jutting out and not below the pair of red lines. Okay, so we can't always win the game for every pair of vertical lines that I give you. So where does all this where does our intuition come into play in trying to trap the function? And this is where the delta-epsilon definition of a limit comes in. And so this is what it really means to approach a value of a function. This is not typically covered in calculus class, but this trapping game that hopefully will give you intuition is really what the delta-epsilon definition of a limit really means. Let's place down some symbols, but we'll relate to how it plays into our diagrams above. So if we have a function, and if we have a function f, and we want to approach a certain x value. So I pick points over here, but we're really approaching a certain x value over at where the function is located. So the x value is going to be, you can imagine it's going to be like a vertical line at where the function is located, right? So the dashed black lines in all three of these diagrams is going to be our x value. So let's say we want to approach a function towards a vertical line x equals a. So those were our dashed lines above. And now let's assume that the limit as x approaches a, right? So this is basically formalizing our intuition that you may have learned from calculus class, that you get closer and closer and closer to a vertical line from both the left and the right. So let's assume that the limit as x approaches a of this function, right? You're traveling along this function. You're traveling along this function from the left and the right. So you're going to walk along this function. You're going to try to approach a from both sides. And let's say this limit attains a value of L. So you seem like you are approaching a value of L. So now what the definition tells you is that if this is valid, then for all epsilon greater than 0, and epsilon is just any positive number. So just think of it as any positive number. It's just a variable. For any epsilon greater than 0, you can choose another constant, delta greater than 0. So you can choose a delta. Again, this is just another variable. You can choose a delta greater than 0 so that this limit exists only if you can choose delta so that whatever I say next is true. So what is that statement? It is if you were to choose a pair of vertical lines with delta to the left and to the right. So again, what did we just do in the trap the function game? We chose a pair of vertical lines. We chose a pair of vertical lines, some distance to the left and some distance to the right. So this is basically what this is saying. here, right? I'm going to use the first example that we covered as an for this definition, just to make everything clear. So x equals a is where we're trying to approach, and the left vertical line is going to be x equals a minus delta. So we can say that this width over here is going to be delta, and this width over here is going to be delta. So it's just how far left and how far right are you going to go from your vertical line. And so because we're going delta to the left, the left vertical line is going to be a minus delta. Similarly, the right vertical line is going to be a plus delta because we're going delta to the right. So this is basically encapsulating both of these vertical lines. So the interval described here is just mathematically speaking, the distance from A to wherever you want to go is going to be less than delta. So you're going to be within, all this is saying is that you're going to be within delta of the value you're trying to approach, the x equals a. So the vertical line. So this is what we're trying to choose delta to. So just to recap, we want this to hold true, and we want to choose delta so that this whole thing holds true. So what is this statement again? It's that if we can choose a window, right? If we can choose a window so that we can constrain it within epsilon of the supposed limit. So in notation wise, it's just going to be like, it's just going to be written like this. And what this definition is really saying is just trap the function. It's just precisely the game that we covered already. So let's just walk through just a small concrete example, just to see how all of these, like epsilons, deltas, a's, and x's all like come into play. Okay, so I'm gonna give you a function here, and let's suppose I want to approach like this point at x equals a. So this vertical line is going to be x equals a. Simple enough. And now I'm going to give you a window, and again I'm gonna assume that we can if we suspect that a function is at y equals L, right? Then we can say that this following point is a comma L. So now let me give you a pair of vertical lines, so that the top line is y equals L plus epsilon, and the bottom is y equals y minus epsilon. So we're going epsilon above and epsilon below. So that's what the epsilon over here means. So if I give you any epsilon, any positive constant epsilon, and I give you a pair of horizontal lines, epsilon above and epsilon below, then the limit exists if you can give me a pair of vertical lines delta from A. So this so the vertical lines are going to be delta from A. So delta to the left, which will yield x equals a minus delta for the left vertical line, and x equals a plus delta for the right vertical line. Right? If you can give me those two, if you can give me a delta so that this function is constrained, then the limit exists. And that's for any epsilon greater than 0. It has to work for any pair of vertical lines. So if I give you stuff like one pair like this, then you can give me a pair of vertical lines. If I give you something like that, still you can give me a pair of vertical lines. If I give you even something like that, like something very small, you can still give me a pair of vertical lines which look like this. So that's basically all that these symbols are saying. So epsilon is just the width, or rather the radius of the horizontal lines, of the pair of horizontal lines, epsilon above, epsilon below. And then delta is the value that you're going to pick. So delta to the left, delta to the right for the vertical lines. So that is basically what trap the function is. It's the delta epsilon definition of a limit. So you may be asking, like, why is this useful in any way? So why do we really need this definition when we can just say that a limit is just approximately the value that a function approaches as you approach a vertical line from the left and from the right. So why do we need to think about the actual definition over here, right? With all of these, even with the game, right? All of these like vertical lines and horizontal lines flying all around, when we can just say that we can approach a value of a function. The reason why we use this epsilon delta definition is that we've picked what a limit is in a well-defined way. So mathematicians have already developed the limit so that it is defined as something, as a value that a function approaches. But to be more precise, this whole definition is what the limit really means. So although limits can be used to define the value a function approaches, we can go from the basic definition of a limit. So this is what the limit like really means, formally, so that we can develop a different set of intuitions. So if we wanted to prove, let's say, the limit as x approaches 2 of x is equal to 2, right? We can't really just hand wave it and say, well, at the line x equals 2, then we obviously approach the point 2, 2, because the function f of x equals x is defined at 2, right? Because the limit might not be defined at the value we're trying to approach. So when we're trying to prove such an assertion like this, we don't need to rely on hand-wavy arguments like saying that the function approaches 2, right, as x approaches 2 because it seems like it. We can actually do it rigorously and correctly using the definition. So just to summarize, how does the function trapping game have to do with limits? Well, the function trapping game is a very useful it's just a very useful analogy for the epsilon delta definition, and that leads to what we know of today as limits. Thank you so much for listening, and I'll see you in the next video.